Okay, so our next speaker is Vineet Tyagi. He is a research associate who is working on the Indo-Dutch project, which is part of the project which is organizing this session. Vineet comes with a background which is slightly different. It's from wealth management and operations, although at some point he decided to change his career track and he joined this group given his love for research and data science. Uh, Vineet comes from, has bachelor's and master's from IIT Bombay in metallurgical engineering, and he's going to talk about neural networks for predicting parameters in pipeline flow modeling. Vineet, the floor is yours. We can see your slides, and I think I still cannot hear you.
Yeah, can you hear me now?
Yeah, sure. Yeah, I can. Thanks, Vineet.
Yeah, so I'm not sure if you can see my camera. I'm not sure if it is working, but I think the audio is fine. So we'll just, yeah,
that should be fine.
yeah, fine. So I'll start. So basically, as Shashi introduced, the broad objective of this project has been to model water pipeline networks. So we right now focus on water pipelines and how we can model them using neural nets and make predictions. So the way we'll go through in this presentation, the structure would be that we first start with understanding very broadly what are we talking about when we say water pipelines in terms of the equations generally being used to explain them or to define them. We'll very briefly see how these equations are solved. Uh, for this exercise, we are using a dummy network, or I would say a very simple layout, commonly referred as Hanoi network. Since we do not have real-time data on this network, we will be generating data using some water management softwares, EBANET being a very popular one. And we'll see that how do we go about generating data using EBANET. And once we have that data, which we think is good enough and which is representative of say near real life scenarios, how do we move to the next step, which is feeding that data into neural nets and learning from the data. So a typical water supply network, as you can see from the picture, so this is a drawing or a layout of a real network, which has been drawn using softwares like EBANET. When we say the draw, basically we are saying that we are giving or feeding in inputs. So we are basically giving inputs to software in terms of elements and then details of those elements. So I have listed all the key elements which define a network. So reservoir is the source basically. Typically it's a river or a lake or say a dam reservoir. Then tanks we have throughout the city or the network, which are basically storing water. Of course, the most important for our experiment in this case has been the pipes, sometimes called links, which are defined with length, diameter, and roughness. Basically, roughness is a function of material and also kind of age in some cases. Nodes basically is whenever two pipes or say other two elements meet, it is defined as node. Nodes are again very important because if suppose you are you're taking out water or you are feeding in water, that measurement of the flow is done at or the pressure is done at the nodes. So these are the kind of elements in terms which we use in terms of defining the network. Of course, there are pumps and valves, but but for this particular experiment, since the layout has been pretty straightforward, we have a reservoir and we have some pipes and nodes. So once we have these elements which define a pipeline network, we'll just briefly see what are the equations that govern the flow, and how do, say, if you're not using, say, a machine learning model, if you're using proper hydraulic equations, what are the equations that play a role in defining the flow and the pressure throughout such networks. So one is, so both these equations are pretty, I would say, intuitive. One is mass balance. So whatever comes in and goes out, uh, net out should equal to what is consumed. So basically, in this equation, the character D stands for demand. So suppose a node represents a point where water is being drawn for, say, a single house, or say for a locality as a whole. So that demands become, so the D represents demand, and Q basically would be the pipe which leads to this node. The two pipes, one coming in and one going out. But there can be a complicated node wherein there are multiple pipes. So that way. And then we also have that, you're given two nodes, or basically 2 points where you're measuring pressures, and they are being joined by an element. For simplicity, let's assume a pipe. Uh, the second equation basically says that the drop in the pressure in these 2 points should equate to, is basically being represented in terms of the friction that this pipe or this element offers. And this second equation, which we are showing, is typically empirically derived. So I have also mentioned very commonly used empirical relationship, which goes by the name Hazen-Williams equation, where you take any two nodes, where basically nodes being the point where you have the head measurement or the pressure measurement, and between these two nodes, you are given the details of the pipe in terms of its diameter, length, and this character C basically is representing the friction. So basically, this is the way these these are the hydraulic equations which will determine the flow. There are some standard methods to solve these equations. I'm not getting into the details of them, but you can see that if the network is large, the number of vectorized parameters can also be pretty large. We'll see that this could be one of the constraints when we talk about really very large networks. But this slide, I just wanted to show that there are pretty standard methods of solving these set of equations. So we won't be going into details here, but the method which EPANET, the software which we are referring to, uses is called Trudini-Pilati method. So here we start with the network which we will be dealing with. I mean to say this experiment deals with. So here you see that compared to a real life network, this is pretty straightforward. So it's kind of ideal to conduct basic experiments, and also to see if these experiments are going in the right direction or not. So here we refer to this network as Hanoi network. It has one reservoir, which you can see as node 1 right at the bottom, and then it has 31 nodes and 34 pipes. So all the nodes are these circle dots, and then the links joining them. So we'll see how this network is defined for a regular software. So the way we define this network is in terms of inputs. If you have in this case, we have 32 nodes. So we need to supply something called the demand at these nodes. So demand is basically how much water has been planned to be taken out at each of the node. So basically, you can assume that at more or less at each node there is a point where the water is being taken out. It could be a house, it could be a locality. Another thing that you need to tell the software is, or to the hydraulic solver, is that what is the head or the pressure maintained at the reservoir. So that is another input. And the third input, which is kind of static, which won't change, uh, is the details of the pipes throughout this network. So when we say a pipe, it is defined by a starting node and an end node, its length, diameter, and its roughness. So once we have given these inputs, we essentially are ready. We have given all the required information to the hydraulic solver, and then let's use the word demand scenario. So this whole thing right on the screen defines a demand scenario. When we change the demand table and we change the reservoir head, we then say that we have another demand scenario. So for a single demand scenario, a single run would from the solver will result in the head readings, or basically the resulting head at each of the node. So basically we are saying that, okay, if we had a network which was like a Hanoi network, and we decided that on each node we are giving certain amount of demand, and then we have a reservoir which is at certain head, and then we just start the system, all the valves open and water starts flowing, and the water reaches steady state. We are asking what would be the pressure at each node and what would be the flow in each pipe. And this is essentially what the software has done for us. It has solved those hydraulic equations, and this is what the output is, that we know that for that particular demand scenario, for that particular starting point in terms of demand and reservoir head, when the system reaches steady state, uh, what would be the resulting heads at each node and flow. So this is the output. Now, the reason I'm explaining these things and also showing little in detail is that these these results essentially will be used later as an input for training a neural net. So basically, if we have a fair idea of how what are the things we are talking about and what are the features we are talking about, we'll be able to understand the content ahead a little better. So this is, we saw that you given a demand scenario, you get an output. Then why should we start talking about machine learning when we have these solvers? So these solvers actually indeed do a good job, but there could be constraints. So, and these constraints will just highlight. I'm sorry for the voice thing. It's a little old laptop, so bear with me. Some people are having issues. So the so one of the challenges that we could face is that there's a dependence on empirical relationships. So we saw that Hayes and William, which is an empirical relationship, is being used to solve for a network. Now, these empirical relationships may or may not hold uh, for every part of the network or for every case. And we know that in general, machine learning models, they don't assume an empirical relationship. In fact, their key objective of using them is that they learn these relationships. So that is one reason. Another reason could be that the properties that these solvers assume, the network properties, when we say we talk about a pipe and we talk about its roughness and in fact its diameter, we know that over time, and the time could be say a few years or say a decade or so, the pipe properties changes because the rust and all. uh, there could be other factors leading to change in the properties and network itself. Then of course, if you have not updated your hydraulic model appropriately, which won't be very easy, the results may not match or may not be the correct one. Uh, in case of machine learning models, because they are not assuming network properties as such, like pipe details and all, this dependence is not there. Lastly, we are also we have seen that on one of the pictures, which is like those lines, it's a very zoomed in picture of a very small part of Bangalore water supply network, and we can see that things get quite busy, even a small part. So if we start feeding in all the details of the whole of a metro like Bangalore and any other city, we can assume that the amount of data we are talking about, the parameters could be very, very large, and it could be the case that the solvers are not fast enough because the calculation could be involving. So that is something which, in general, we have seen that the machine learning models can be much faster than equation being solved by algebraic methods. So these are the broad reasons we think that machine learning could be doing a better job. For this particular case, this experiment, we are using neural nets. So I won't be going into the reason why neural nets and why not something else. But people have been working on this problem and they have used other models. So I think neural nets being commonly used nowadays, we thought we'll try them out, and we'll see the results. So we have covered when we say water supply network, what are the things we are talking about? Uh, what is the kind of data we are talking about? Now we'll go to the next phase of this exercise. Is saying that if we have a software like EPANet and we can generate data, then how do we go about generating data? So the first step that we do is we said that one demand scenario gives us one set of solution in terms of flows and heads, but in a real network, during a day or over time, uh, there could be various demand scenarios, particularly when the supply is not constant, and in fact the demand keeps changing. So we want a model. We want to train the model in such a way that it can work with various demand scenarios. So different demands, different demand combinations across the network. To create those scenarios, what we did, we started with the base scenario, and then we used a very simple covariance matrix, and we generated a lot of normally distributed demand scenarios. So basically, we are saying that you start with a base, and then you generate basis that base and a covariance matrix. You can generate a lot of scenarios. Although what happens is, the first step we generated like 100,000 scenarios, and we realized that a lot of them had negative demands. So negative demand is not something that that we'll work with, because that doesn't exist or that is not suitable for this thing. So we filtered them out, uh, and then after filtering them, we had say if we start with 100,000, we'll be left with like 30-40,000 odd, or say 20,000 odd cases where all the demands are positive, and we feed in these demand scenarios across the 32 nodes that we have into EPANet and generated the resulting flows and heads. Uh, Again, after this generation, we realized that there were certain cases where the resulting head was negative. So when we see if we go into the details of hydraulics, we'll see that these softwares, when they result in a negative head, basically they are saying that this particular kind of demand uh, uh, demand scenario can't be met with the sources, with the water source and the head you have. So basically we took them out. So basically these are the scenarios which are again infeasible in a real life situation or from
Vineet,
hydraulic perspective.
sorry to interrupt. I
Yeah,
think your slides are
yeah.
not moving.
So, is it
Oh,
moving now?
okay, okay. Yeah. Oh, okay.
Sorry, yeah.
Sorry,
So
sorry. I thought you were.
explaining a little further. Yeah. So basically, so what we saw so far was that you have a software and then you start with the starting cases, and then you generated results from those cases. We just want to have a quick look at what kind of distribution we had. So there are like 32 nodes. I have taken 6 of them. So so first is in node 2 and then node 8, node 15, just some random cases, just to show that we have a near normal distribution. uh, just gives us a little more flavor into the kind of data we are dealing with. uh, so we see that the demands, so here the in terms of units this is a liter per second. So different nodes may have little different demands, uh, and with those demands, and when we saw the result, so basically here these are the histograms on the x-axis. We have either the demand in terms of in liter per second. When we talk about flow rates, again in liter per second the flow, and what we have on the y-axis is the frequency throughout our. We have like 5,000 odd samples, so the frequency of those kind of flow rates. uh, and so this is the data we have. So we have around like 5,000 odd cases, and each case basically has uh, a demand scenario which resulted in nodes and flows in those 32 nodes and like 34 links. So basically this way you will see that you have some 90 plus columns and like 5,000 rows kind of data. What we so when so this is what this is our raw material for the experiment. Now to try out a neural net, what we did was we started with a very basic setup. We said that for a hydraulic model, suppose we are trying to solve a very basic problem, and this problem can be defined with this figure on the slide. We input uh, pressure or the head at 2 nodes, and we want to know that what happens between these 2 nodes. So how the flow happens when so we have the data. We know that uh, we have like 5,000 cases for which we know that if there is a, so if you refer to the figure, uh, the head at node 31 and head at node 29, if it is given, I know what is the corresponding flow in link 31 and link 32, and I know what is the corresponding head in node 30. And this has been this is the result from a hydraulic solver of the Ethernet. We want to see if a neural net can learn this relationship. So we just divided. We had a train test and a test set, and our objective was that you given the head at node 31 and given you give the head at node 29, can your model learn what should be the flow in link 31 and 32? So this is how we designed the experiment. Just we had one another detail. We also, as an input to the neural net, we also gave the demand at node 30. So basically we are saying that I'm training the neural net in this particular way. The objective of this exercise we'll see when the network becomes a little larger. I will show you uh, two scenarios, or basically two examples. So one was a rather small part of the Hanoi network, where we are saying that can a neural net learn the relationship between the nodes, the nodal heads and the flows. Another example had a little larger area where again we wanted to test the same thing. And if I just get into little more detail in terms of input and output, in the first example, we are to the neural net we are feeding in the headset node 29 and 31 and the demand at 30, and then we are trying to predict flows in this circled area. Similarly, we are giving in the next example, we are feeding in the heads or the pressure at node 20 and 26. So you can assume that maybe in the real life scenario you have only two sensors, and then you say want to understand what's happening in the other part. Although I mean you have the readings in the other part also. So how do you is your model able to learn the how the hydraulic equations work when the unknown network is a little larger? So this is how we define the problem. Uh, so here I have shown the results for example A graphically, and if we see the results, the left-hand graph, which reads the ground truth, is basically if I plot the Hazen-Williams equation, where the delta H is related to the flow in a pipe. So we'll see that there is a relationship with that which had flow raised to the power 1.85, something like that. So the ground truth is this is the kind of graph, or this is the kind of fit I should get. On the right side is a prediction for case A of a neural net which is not very deep, and we see that the fit is fairly good. Here the R squared errors are like close to R squared is close to 1. If we talk about the larger network which we had seen, which required the neural net to predict much more, even there we see the fit is fairly well. The model is able to predict the heads pretty nicely. The quality of prediction relatively goes down in case of flows, but even then they are pretty good. So what we understood, our kind of takeaway from this set of experiment was that if you design the problem the way I had explained, um, you given if you know the demands in the network, and you just take any two nodes and say, okay, these two nodes is what I am feeding into the network. Can the neural net tell me what's happening in the rest of the network? The neural net can be trained to make good predictions. So this was our broad takeaway. Uh, I'm sorry, I'm moving a little fast here. There's another set of experiment we did. We said that suppose the demands are not known. So basically, we are saying that we don't know in the network what are the demands, but we know that we have a lot of flow and head readings, and with these flow and head readings, we are trying to understand the network. What we saw that in that case, the prediction quality goes down. A neural net is I mean it's difficult to make the model learn what will be the flows and the heads in the network if you are not giving the details of demand. So this was from the hydraulic perspective, it is kind of uh, intuitive, but I just wanted to to show this graph. And we can also see on the table on the right hand side. Yeah.
Vineet, I think we are overshooting on time. So if you could wrap up,
Yeah.
quickly, it would be great so that you can take some questions as well.
Sure. So basically, this was these two experiments. Very quickly, I'll just go through another set where we introduced. We said that okay, suppose the neural nets are working fine, and what if you are posed with the problem of say detecting leak or some anomaly in the network? There, I'll just quickly go through the last slide. Basically, this is very similar graph which I just shown you. Here, without getting into details, these star marked observations are basically the flow in a given pipe when there was a leak, and these blue dots are uh, the kind of predictions which the model would make. So broadly what we see is that if the leak is high, uh, uh, or decently high, then the observations of the sensors, the data that sensors show, would be pretty far off from the predictions which a neural net would make. And it could be possible that we can use such a neural net to detect anomalies in a pipeline network. I'm sorry, so we'll just without getting into further details, I'll just wrap it up. So we can kind of ignore the last part, this lead part, and we can maybe talk a little further through in the question answer session on the other experiments. So thanks, Shashi. We can go ahead.
Yeah. Thanks, Vineet, a lot for the interesting talk. I think there were a few questions in the meantime. I think the first one was from Root. He wanted to know what type of empirical correlation is currently used in your neural network model, in your network model.
In the neural network, we are not assuming empirical relationship for the data that we generated to train the model. We are using His and Williams.
My question was about the basic model, not the neural network model, but just your basic network model.
I'm not very sure of the question still. So basically, I'll try to answer maybe if that is correct. When you wanted to generate the data using the hydraulic model, before going into neural net, we use EPANET, which had the option to choose among three commonly used empirical relationships. So we chose His and Williams. So basically, and I have just on this slide, which is right in front, I just mentioned.
I think it's more about empirical correlations.
So it is the Haven-Williams correlation. That's the empirical correlation that you use for the wall friction, I guess.
Yeah.
Okay.
Hey Vineet, Amritendra here.
Yeah.
Thank you.
I have a question.
Yeah.
Why do you say that R square error? Because R square is not an error. It should be either RMSE or you can say rho. R square error, I don't know. I mean, could you please explain what do you mean by R square error?
No, so basically we started with RMSEs and all, but these things are anyways related in the sense that we wanted a unit test.
You not get my question. What I'm saying is R square is not exactly an error measurement. That's what I'm trying to say.
So I mean so you can say an accuracy measurement, if not an error measurement. What I meant to say was that we wanted a unitless measurement to see what is accuracy across node and flow.
R square is a measurement of you basically, I mean, percentage of variability that you can explain in that model. Nothing to do with error actually. Anyway, okay, you might like to check that once.
Okay, fine. I'll just make a note and I'll see if yeah.
So there are a few more questions. I'll just pick one more, and that is, can you explain why you are using neural network here? You can use a 1D network solver for solving your problem, and the question is, why do you want to use a neural network?
So if the question is if the question is more to do with why neural net versus a basic hydraulic model, basically on this slide we are making some observations in general that if we are talking about I say a pipeline network, or say any physical setup where a solver or hydraulic solver is assuming some empirical relationship. And a machine learning model in general and neural nets also, they don't assume uh, such relationship, they deduce them. So that is kind of advantage, and there are other advantages which are listed on this slide. If it is, the question is more to do with why neural net among machine learning models. So there is no hard and fast reason for it. Neural nets have been doing a decent job when it comes to learning non-linear relationships in other parts, or other parts of studies. Uh, so we thought that, if they're doing well there, they will do well here too. But people have used SVMs and other uh, proven machine learning methods to solve similar problems. Machine learning. So this is just, just a choice, and no hard and fast reason for it.
So I see it as you want to replace the network, especially if you do not know how the ground network looks like, with more sensor driven data. And in that case, it might not be possible to solve the 1D using the 1D solvers, right? Would that be?
So that is one big advantage, in the sense that, there could be cases or situations wherein all the details of, or the minute details of the network are not known, which may be required for a regular hydraulic or a 1D solver. But just with sensor data and machine learning models, maybe you can do away with knowing everything and still solve your problem.
There are a few more questions around here, but I think it would be good if those questions are answered offline, so that we can move on to our next speaker and be still on schedule. Our next speaker